All right, I guess we'll get started. There we go.
You want the lights off?
I don't think it matters. This TV is bright enough. Usually we turn the lights off for the projector to get the better image, but this is okay. So welcome to our October 2nd Saturday Stars. My name is Mark Polanski. I've been a volunteer here at the observatory for about 10, 11, 12 years. I kind of lost count. I've been imaging for about 10 years. Recently, I picked back up again with planetary imaging, so tonight's presentation is a guide to planetary imaging, or all the things I wish I knew when I got started. So, a primer on astrophotography. It's generally split into two categories. There's deep sky and there's planetary. Deep sky generally focuses on things that are outside the solar system, galaxies, nebula, things that are much more distant and therefore much more faint than the relatively large objects in our solar system. So deep sky requires much longer exposure time, measured from seconds to minutes versus the milliseconds of planetary exposures. It requires precision tracking, typically with a special guide telescope to keep the telescope pointing in the right direction for long enough to get those long exposures. Cumulatively, you're talking about hours worth of exposure time. Like this image of the Veil Nebula that I took a couple weeks ago is about 6 hours of total integration time. And the best processing software can be expensive. I use PixInsight as my personal processing program, and it costs around $300 to license that. Planetary focuses on objects within the solar system, most commonly Mars, Jupiter, and Saturn, and of course the Moon. Sometimes you can get away with a single shot if the object is big or bright enough, like in this case the Moon is a single shot through a Canon mirrorless camera mounted to a telescope. We're talking very short exposure times measured in milliseconds most of the time. A tracking mount is nice, but not 100% necessary for planetary imaging. Cameras are also relatively inexpensive. A good deep sky cooled camera can be maybe $1,000, $1,500. A really good planetary camera can run about $200. And the best processing software is free. I use AutoStacker and Registax for most of my workflow. So what do you need? What does it take? Really all you need is a telescope and a camera. Generally with the telescope, you want to have a longer focal length for more magnification, and we'll talk about that more later on. And you want a large aperture to get more detail. For the camera, you can get away with a digital SLR or a mirrorless camera to get single shots of some of the brighter objects, but you're going to get better results with a specialty planetary camera using video. Some other stuff that's really nice to have. Because your camera's mounted directly to your telescope, you can't really change the focal length. You can't magnify it. If you're looking through a telescope visually, you can swap out eyepieces to get more magnification. You can't really do that with a camera without using a Barlow lens or a focal extender. A tracking mount is also helpful for keeping your object in your field of view for longer, so you can take longer videos and get more images. An electronic focuser is really nice to avoid vibration. At high magnification, if you just tap the telescope, it's going to shake violently like an earthquake. And a laptop or a PC helps to be able to see what you're doing in real time. You can adjust your focus and you can capture your images and do some live stacking to get a good idea of what you're looking at. Other necessities. Good sky. And I can't put enough exclamation points on that because that's what really matters when it comes to planetary imaging. And that doesn't just mean clear, not just cloud-free, but also stable. This is by far one of the most important things for good planetary imaging. It's also known as seeing conditions. The other important thing is thermal equilibrium, meaning your telescope has to be at ambient temperature. You also want good optics. You want your telescope to have a good quality mirror or a good set of lenses, and it must be perfectly aligned or collimated and focused really well to get decent results. Above all, you need patience. Back in 2013, I gave up on planetary imaging because this was the best I could do, and I was never really happy with it. This was taken through the 16-inch here at the observatory. And I got frustrated because it said, well, we have this big telescope, how come it can't do better? I just needed to learn. So let's talk about the telescope. Telescopes are measured in two primary factors. You have your focal length and you have your aperture. Your focal length is basically what distance the telescope optic needs to bring incoming light to a focus. In terms of planetary imaging, it means how big something will look. It's your magnification. Again, for visual magnification, you can modify that based on what eyepiece you put in. But for planetary, with the camera directly mounted to the telescope, you're kind of stuck there without using a Barlow lens. Aperture is basically how big your telescope optic is. It's either your primary lens or your primary mirror. Mirrors are generally easier to make than lenses, and they can be made by hand. So most of the larger telescopes use mirrors instead of lenses. It also defines how much detail you can actually see. This is known as the Dawes limit. Telescopes are mostly described in terms of their f ratio, which is your focal length over your aperture. So you might hear someone say, I have an 8-inch f5 or an 8-inch f10. If you multiply the aperture by the focal ratio, you get your focal length. So an 8-inch f5 would be a 40-inch focal length, an 8-inch f10 would be an 80-inch focal length. So with most reflector telescopes like Dobsonians, with a classic Newtonian reflector, your focal length is going to basically be the length of the tube of the telescope. So if you wanted a longer focal length to do planetary imaging, like an f10 8-inch Newtonian would be roughly 80 inches in length, which is taller than most people. You can't really look through that, or you need a ladder or a step stool to really use it. So there's an optical design called the Schmidt-Cassegrain, which by using different types of mirrors and a corrector plate can squeeze a very long focal length into a very compact package. Makes it great for portable telescopes and getting really long focal lengths in a reasonable size. So our 16-inch here at the McCarthy Observatory is a 16-inch f10 telescope with a focal length of 160 inches, but the telescope obviously isn't 13 feet long. So aperture aside, it doesn't matter how big your telescope is if your seeing conditions aren't great. So here's some examples of different focal lengths. This is the same camera mounted on different telescopes or different telescope combinations with Barlow lenses to get different focal lengths. So Jupiter at a 275-inch focal length is obviously bigger than 200, which is bigger than 80. Aperture and the Dawes limit. The Dawes limit is an approximation of resolving power measured in arc seconds. We measure the sky in angular size, degrees, arc minutes, arc seconds. Think about looking at the horizon and then looking straight up. This forms a 90-degree angle. We're talking about our subsections of that angle to measure the relative size of objects up in the sky. There are 60 arc seconds in 1 minute, and there are 60 arc minutes in 1 degree. So the formula for the Dawes limit is either 4.56 divided by the aperture in inches or 116 divided by the aperture in millimeters. So what you can see for detail is entirely dependent upon your aperture, regardless of your focal length. So objects in the sky are also measured in angular size, but that can vary depending on how close the thing is from Earth. For example, Jupiter at opposition, when it's at its closest approach to Earth, measures about 49.5 arc seconds. When Jupiter is on the other side of the solar system, it measures about 32.7 arc seconds. On average, the Moon is about half a degree, or about 30 arc minutes in size, for some comparison. So if we know the actual diameter of an object, along with its apparent size in arc seconds on a given date, we can calculate the rough size of details we could possibly see based on the Dawes limit for a given telescope size. If we divide the known object diameter in miles by the angular size, we can get how many miles each arc second represents for that object. So for my 11-inch telescope, the smallest theoretical features I might see on the Moon are just under half a mile. So what might that actually look like? Here's a mosaic image of the Moon I took a couple weeks ago. It's 11 images processed and stitched together to produce a really high-resolution image of the Moon. So if we focus on that yellow square and zoom into the full resolution, this is what it looks like. So in theory, according to the Dawes limit, some of those smaller features, those smaller boulders, craters, little ridges on the Moon, could be as small as a half a mile in size. So given this, what's the most common question that astronomers usually get when talking about telescopes and the Moon? Can we see the flag? I did some math. The flag is about 61 inches wide at the diagonal, which is just under 1/1000th of a mile. If I work backwards using the Dawes limit, I found it would take a 435-foot or 133-meter aperture telescope to see the flag as the tiniest possible speck on the lunar surface. The largest optical telescope in the world is currently under construction in Chile, That's the extremely large telescope with an aperture of a mere 39 meters or 129 feet. And this may be the largest possible mirror we can work with on Earth, given structural limits and trying to keep everything as precise as possible. So, no, we're not even close to being able to see the flag from Earth. So let's talk cameras. Most people think of photography as just snapping a picture, like you're done. When it comes to planetary imaging, video ends up working out significantly better. Because video is an illusion. It's flipping a bunch of images really fast to make it look like things are moving. The word movies is derived from moving pictures. If you've ever played video games, you might worry about FPS, or frames per second. If your FPS falls under 30, the motion gets really choppy. If you're above 60, it looks really smooth. We get the same idea of recording videos. By recording videos, we are taking potentially hundreds of images per second. So why do we need that many images? Because of atmosphere. Between us on the ground and space, there can be anywhere from 50 to hundreds of miles of air. Air is a fluid. It's always moving, especially in the upper atmosphere. The jet stream is a river of air. If you've ever been on an airplane and experienced turbulence, you have felt those pockets of unstable air. Unstable air makes objects look like they're underwater. They're always moving, they're always shifting, but sometimes for fractions of a second, the air stabilizes long enough to capture a decent image. The idea is if we can capture many images as fast as possible, some of them might catch those moments of stability. With planets in particular, we call this technique lucky imaging, meaning if you're lucky, out of 20,000 images, maybe 5 to 10% of them are good. They catch those stable moments where you get sharp images free of stretching or blurriness from the atmosphere. The best results come from specialty cameras that are made for this purpose. They have high sensitivity and they can capture at a high frame rate. You usually want to use the highest ISO or highest gain setting you can with the shortest possible exposure to catch those brief windows of clarity at the highest frame rate possible to get as many images as you can in a short period of time. You want to use uncompressed video. You don't want to use JPEG, MPEG, or any other form of compression because compression makes things nice and easy. Like it makes the images small enough to send or share easily, but you lose a lot of extra data that's necessary for image processing. The specific settings, like the specific exposure and gain settings, vary by camera, so I can't really go into details there. But you can get some decent results even with a DSLR or a mirrorless camera. I have a Canon R6 mirrorless camera that can record 4K video at 60 frames per second, and that's a high enough frame rate and a high enough resolution to get some decent images and stack the images together. The other nice to haves. We talked about focal length. The only way you can really magnify the image produced by a camera is by using a Barlow lens, if your aperture and scene conditions support it. Sometimes it's not worth making something bigger if you're not going to get more detail out of it. Sometimes if you make something bigger, if it looks bad, it's just going to look worse when you make it bigger. Most common types are 2x, 2.5x, 4x, and 5x. Those are multipliers on the f ratio, which applies directly to the focal length. So like an 8-inch f10 telescope, if you throw a 2x Barlow on it, it becomes f20. Therefore, the focal length goes from 80 to 160 inches. Tracking mount doesn't even have to be equatorial, just something that keeps the object framed and centered, or at least not drifting out of the field of view often. You can use a Dobsonian or a non-tracking mount, but you have to use what's called the drift method, meaning you would position the telescope just in front of where the planet's going to end up moving, and then let it drift through the field of view as it follows Earth's rotation. Then you'd have to move the telescope again, get ahead of it, let it drift through again. So you can get some decent results from that, but it's way easier if you have a mount that can keep it centered. An electronic focuser helps you significantly at high magnification, because every time you're adjusting the focuser, either turning the knob on an SCT or turning the rack on a refractor, every time you touch that telescope, it's going to start shaking. And it makes it really difficult to see if things are in focus if they're constantly moving. You also get finer control. Sometimes the difference between in focus and out of focus can be measured in micrometers or almost nanometers. And you don't get that kind of precision if you're focusing by hand. You also want to use a laptop or a PC. Most of the specialty cameras are going to be USB anyway, so they'll need a PC to operate. But you can see what you're doing in real time. It's really easy to focus when you can kind of focus while you're looking at the screen or using the electronic focuser on the computer without having to bump the telescope. You also get to see your results in real time. You can see the video stream coming in, and you can pretty quickly tell if you're in focus, out of focus, or if seeing conditions are good or bad. The really important stuff, again, seeing conditions, doesn't just mean cloud-free. Stable air is absolutely crucial. You want little to no wind at ground level because that alone will vibrate your telescope enough to cause problems, but also in the upper atmosphere. The object altitude, how high does it appear in the sky? Usually the higher you're looking, the less air you're going to be looking through, so you have less of a chance for that turbulence to interfere. Thermal considerations. If your telescope is inside most of the time in your house and it's a balmy 70 degrees, and you take it outside in the fall, if it's 40 degrees outside, now your telescope has to adjust from 70 degrees to 40 degrees. It may feel like it adjusts pretty quickly if the tube has relatively thin metal. If you touch it, it might feel like it's at temperature. But you have this big, thick piece of glass in the back if you have a reflector telescope, and that thing can take hours sometimes to get down to temperature. If it doesn't get down to temperature, what happens is the air inside the tube will cool down as it makes contact with the air surrounding the tube. But because the mirror retains that heat for much longer, it ends up heating up the air. The air rises within the tube, the cool air settles down below it, and you end up with a convective cycle. And that convective cycle can appear to be turbulence in the atmosphere, and it just makes your images look like garbage. You can never get good focus. You can never get, things looking just right until that mirror has cooled down. Objects in front of your telescope can have the same effect. When I was playing with one of my new telescopes, I took it to my office to try to collimate it using an artificial star, where I have way better control over the ambient air environment. I could turn off the HVAC and have a nice stable environment to play with it. I'd set the artificial star up far enough away to bring it to focus, and I would see the collimation pattern. And if I just held my hand in front of the telescope, I could see the air radiating up from my hand through the camera. So houses, trees, pools, anything that might retain heat that's close enough to your telescope is going to cause problems. Collimation. A telescope is like a fine instrument. If you play a piano and it's slightly off key, you can kind of hear the song, but it doesn't sound great. Telescopes kind of operate the same way. You need to have the optical axes fully aligned as perfectly as they possibly can be. Those mirrors have to be perfectly aligned to allow that light to focus to the right point. The best way you can tell if a telescope is in focus or collimated is to point it at a really bright star and rack it in and out of focus. And when a telescope is at focus at high magnification, the star is going to take on this bullseye appearance that we call the airy disk, where you'll have a bright dot in the center and then concentric rings of diminishing brightness around it. If you get that perfect bullseye pattern, it means your telescope is very well collimated. Now, this is tricky sometimes, especially outside, because, again, the air is always moving. So this is what you end up seeing when you're trying to collimate. Sometimes you'll get those moments where it's clear and you can really see that bullseye pattern, but for the most part, it looks like a jumpy mess. And if seeing conditions are poor, you won't even see that at all. It'll just look like a blob of light kind of sparkling. So that's part of why it takes patience and it takes time to get a really good night to be able to fully collimate your telescope. So here's an example of poor to fair seeing. This is the raw video, and that's the resulting image that was stacked from it. I don't know why the TV is making it look blocky like that. It doesn't look like that on my screen. But you can kind of see that the rings themselves kind of blur in and out sometimes. You can't really see any division. You can't see that division between the rings, except for those occasional frames where it snaps into focus. The resulting image is not terrible, but it would be better if we had better seeing conditions. Here is some just straight poor seeing conditions. Jupiter just kind of looks like a blob, not a lot of detail seen. Once in a great while, you'll kind of see the bands kind of snap in, and the image kind of speaks for itself. If we compare that to a night of good seeing, it's a fairly dramatic difference. And you can even see on the raw video, again, I'm not sure why it's blocking out on the TV, but if you focus on the great red spot, you'll see brief moments where it becomes a clearly defined circle with a very sharp edge around it. Along the top of the planet, you'll see one of the upper equatorial bands just kind of snaps in and out of focus. So those are signs that you're seeing is okay, even though it's still jumpy, it's still kind of blobby. It's those brief moments of clarity that make all the difference. This was a night of good seeing. The moon is still jumping around because the air is still there, but the way you can tell is if you focus on one of the smaller craters or smaller details, it's persistent. It's there more often than not. In poor seeing, you would see those details briefly, but when they're more persistent like that, it means that the sky is stable and you could get a pretty good result. Single shot versus stacked. This is the same camera on the same telescope on the same night. The single shot was a raw image that I processed in Photoshop. The video was taken at 4K 50 frames per second, or 60 frames per second, about 45 seconds worth of exposure time, and stacked together. You can tell the quality difference in clarity and detail with the stacked image. While the single shot may have slightly better color and slightly better contrast, it can sort of pull some of that out by processing in Photoshop on the stacked image. But the big difference I wanted to highlight was just the clarity and the features are much sharper with the stacked image over the single shot, because that single shot is subject to the turbulence and distortion of the atmosphere, whereas the stacked image, that sort of averages out over time. Processing, capturing, and software. So obviously capturing is the process of recording the images or videos. I use SharpCap, which is Windows only. It has a free basic version, but I use the paid version, which is like $20 or $30. It's not much. The Pro version has some nice features for deep sky imaging, but for planetary capture, the basic version works fine for most uses. Firecapture is another popular program. It's multi-platform. It runs on Mac, Windows, Linux, Raspberry Pi, you name it. Apparently it's easier to automate, but I haven't spent a whole lot of time playing with it, but it's also free. I use Backyard OS to control my Canon camera. You can plug in a USB cable, or the newer cameras can connect over Wi-Fi, and you get full remote control over the camera, which makes it way easier to adjust settings without having to fiddle with it while it's on the telescope. I use AutoStacker for basically the entire bulk of the workflow. It does the video analysis, alignment, quality, sorting, stacking, all that fun stuff. And it can even do some rudimentary sharpening to get a preview of what you might get later on. I'll take the output from AutoStacker, feed it into Registax. Registax has been around for about 15 years, and it probably hasn't been updated in as long, but it still works great for what it does. It has a feature called wavelets that allow you to adjust different levels of detail at different layers of the image. It can also do some basic color correction, some gamma correction, and other things that make it useful. So for the most part, the image coming out of Registax is going to look pretty good. But if there's any additional cleanup or any other color balancing I want to do, I'll pull it into Photoshop and make some final adjustments there. So I was going to try to do a live demo if we were outside with the telescope. I was going to bring my 8-inch and my camera and try to actually run through the whole process of capturing and stacking. But since we can't, I'll just go through the stacking process. So I'm going to pop into AutoStacker. I'm going to open up one of the files. So this is what it looks like raw. This is Jupiter from about 3 or 4 weeks ago. Again, you can see that atmospheric turbulence. You'll also notice it's black and white, and that's because this is a color camera, but the raw capture from the camera ignores the internal filtering. This has what's called a Bayer filter, where it separates individual pixels into red, green, and blue, layered over the top of each pixel. So the raw data ignores that, because it's assuming that as you process it, it's going to put that data together and assemble the color image, and AutoStacker does that. So I'm going to open my image in AutoStacker. So AutoStacker automatically detected that there is a Bayer filter in place. So it shows me it's got the blue, green, red pattern on it. And you can see it's now showing up in color. Most of the time, the default parameters are going to work great. It's going to ask you if this is a surface. You'd use surface for lunar images, or planet if it's a planet, which obviously this is a planet. Quality estimation is the default. This is how it determines how noisy the image is, or you can tell how noisy the image is and how that affects the processing. So I'm just going to click Analyze, and it's going to go ahead and look at each frame of the picture, or each frame of the video. There's about 17,503 images in this video. And it's going to compare the images pixel to pixel and look at where it has the highest contrast. And it's going to use the highest contrast as a measure for how good or how sharp the image actually is. So now it's going to sort the frames by highest quality to lowest quality. So it's determined this frame is the highest quality image. And you can compare that to the last frame, which is the lowest quality image. So that just looks like a white blur. You can barely make out the equatorial bands. So first frame, last frame. It's quite a difference. So in theory, it has sorted all of the frames by quality so that the top percentage of quality is going to be in the front half of this image queue. So next thing I want to do is place some align points, and these are going to draw boxes that it's going to use for reference to compare image to image to see what areas of the image are correlated to each other so we can average them together. For Jupiter, especially at this focal length, I like to use about 500 APs, align points. And then I would choose my percentage of frames to stack. I'm going to say I'm going to use 15%. You can usually kind of tell by scrubbing through this and seeing where your quality drop-off is. You know, once you start seeing those details kind of fade away, that's kind of where you want to pick your point. I try to target about 1,000 frames or more if scene conditions support it. Any less than that, and when you go onto the wavelets, you're going to start to see little artifacts and weird things kind of happen. So put the grid back there. With the sharpen checkbox, it's going to produce a internally waveletted image or a sharpened image. It's not going to be as good as what we can do in Registax, but again, it just kind of gives you an idea of what it could look like. RGB align helps you if you have a lot of chromatic aberration in your telescope. If your red and blue don't quite focus to the same point, you might see like a red tinge or a blue tinge on the outside of that. This can help correct for some of that. And the rest of this is pretty basic. If you click on stack, it's going to start stacking. This will take about 3 minutes for this image, so I'm not going to do that because I already did it earlier. The result comes out in this ASP15 folder. This is the raw unsharpened stack. It still doesn't look great, but when it gets sharpened, a little bit more detail comes out. And I can pull out a lot more detail once I pull it into Registax. So if I open Registax and I pick that non-sharpened image, that's what we start with. And then there are 6 different layers of wavelets that can be applied. And these are algorithms that look for slightly different pixel values or pixel correlations. And it can be used to pick out what are called different levels or different layers of sharpening. So each of these brings out slightly more detail. And you'll also see that it starts to get noisy and grainy as you bring this detail up. So here's the before, and here's the after. So if I want to clean up some of that noise, I can turn up the denoise parameter. That'll help smooth some of that out. And you just keep playing with this. You can adjust how much it's sharpening. You can bring some of these faders down or up to see what difference it makes. So that seems to make it noisy, but not really add a whole lot of detail, so I might leave that fader down a little bit. If I bring this down and bring this up, you can see what the difference is. So that I might leave there. Bring this down, bring this up. That's not too bad, so I'll leave that up there. So there's no one right way to do this. This is entirely personal preference and what you want to get out of your images. So I might leave that something like that. And what I'll probably do is go into RGB balance. I can see the blue is offset from the red and the green a little bit. I'll let it auto balance. That helps correct the color a little bit. So before, after, before, after. When I'm finished, I'll say do all, even though it pretty much does everything because the image is small enough anyway. And then I'll save it. So that's the gist of the image processing. So again, above all, you need patience. In this area of the country, good nights are very, very rare. I can literally count on one hand the number of really, really good nights I've had for planetary imaging. There's some pretty good forecast tools on weather.gov that can help kind of determine if it'll be a good night or not. They usually look at the upper air current maps, and the Storm Prediction Center has a pretty good 3-day outlook of 500 millibar level winds, which are somewhere around 5,000 to 10,000 feet. So if I see that there's a lot of upper level winds, it's probably not going to be a good night. So I'll probably focus on deep sky instead of planetary. You got to let it chill. You got to let your telescope come down to ambient temperature. Otherwise, those thermal currents inside will make you think that either the telescope isn't focused, isn't collimated, or that seeing conditions are bad, when really it's too warm. That's one of the biggest issues we have here at the observatory. That 16-inch mirror is massive and dense, and it takes forever for it to come down to temperature. Compounded with the aperture, the dome has a very small slit. If the temperature difference under the dome is different from what's outside, there's going to be a thermal current cycling within the dome itself, which can cause problems. Collimation takes forever to get right. Sometimes it takes a full night on a good clear night or a good stable night to get that done. So of those handful of good nights per year, I might sacrifice one of them just to get the collimation right. Because if you can't see that perfect bullseye pattern, you don't know if your telescope is collimated. And sometimes you can't tell if it's just seeing conditions or thermal, or if your telescope actually needs collimation. When you're collimating, you're basically adjusting little screws on the telescope. And sometimes it can take as little of a 16th of a turn to go from really blurry to really sharp. So that's what really takes that time, is just moving back and forth, seeing what the difference is. When you're focusing, on a planet especially, sometimes you saw in the video, you can't really tell if you're focused or not. It just looks like a white blob. It helps sometimes to increase your exposure time so you can see if there's any moons nearby. Focus on the moons, because they're as close to point sources as you can get at that exposure setting. So as you're racking focus in and out, you'll see the moons get bigger and smaller as they're wobbling around in the atmosphere. So if you can get them as small as possible, that's how you know you're pretty close to focus. And part of being patient means waiting several seconds, sometimes up to 30 seconds between making adjustments. You tweak your focus, watch the result, because you can only really tell how good it is when you get those brief moments of stability. Processing. A large image can take up to 30 minutes to run through AutoStacker, and especially for lunar images that the high resolution, it takes a very long time for all those line points to work their way through and for it to analyze the image. So like that 11-panel moon mosaic took several hours to process because it took about 30 minutes for each image. Progress can be slow and frustrating. I learned a lot online from some of the great planetary imagers. I learned the lucky imaging technique from Christopher Go. I learned proper collimation techniques from Terry Lavelle. And Damien Peach is just a legend. He has a 14-inch Edge HD Celestron telescope, and he's producing Jupiter images that look like they're from Hubble. Because he understands the process and he shares a lot of what he's figured out over the years. So I started in 2011 with a point-and-shoot camera, just pointing through an 8-inch Dobsonian telescope. 2012, we picked up a planetary camera here at the observatory. It was an ASI 120 MC, which I think is somewhere on the shelf or somewhere in one of the drawers. And in 2013, I got frustrated because that's the best I could do. And I thought I was doing something wrong. I thought the instrument was bad. I thought, all kinds of other things, and that this was a waste of time. Until I learned patience and learned from Terry and Damien Peach especially that these instruments can do good work if they are properly taken care of. So 2020, I started to figure that out. I took my 8-inch Celestron telescope at home. I took the time to collimate it, took the time to focus it, took the time to figure it out, and I started getting better results. 2021 got even better. 2022 got better still. 2023 I picked up a bigger telescope. I now have an 11-inch Edge HD. And I've only had it for about 2 months, and I'm still learning what it's capable of. I'm still playing with the collimation, I'm still tweaking it, trying to see what I can do with it. Same deal with Saturn. I tried imaging in 2016 again, and again was frustrated that, sure, you can see the rings, but you can't really see the division of the rings very well, the Cassini division. 2020, picked it up again, got a little better. 2021 got a little better. 2022 got a little better. And that continues until this year, too. In 2020, I managed to get a pretty decent image of Mars. There's a tool on JPL where you can actually look at what face of Mars is facing you and have some fun comparing the features to see if what I was actually seeing was real or if it was just artifacts of the image processing. And it was all real. Last year in December, there was a conjunction of the Moon and Mars that I managed to capture both in the same frame. So that was pretty fun. Kind of a difficult difficult processing because the Moon is so much brighter than Mars. I had to take 2 different sets of images, one on Mars and one on the Moon, process them separately, and then combine them based on their relative positions. Any questions?
Yeah, I got 2 questions, actually.
Well, see that his hand up first.
Okay. When you're collimating, are you using a camera or are you using your eyeball? And if you collimate one way, will it still be applicable to the other way?
Yeah. So to answer the second question first, it should still be applicable, assuming that everything optically is aligned properly. If you're sticking the camera into the eyepiece holder in the same way that you'd stick an eyepiece, then theoretically the collimation should be pretty similar because everything should be aligned properly. If we're using a diagonal, it gets a little bit odd because depending on the shape of the diagonal and where it specifically is, it might be a little bit different. But for the most part, for visual observing, collimation is slightly less important. I mean, you're going to maximize your detail if the telescope is perfectly collimated, but if it's well collimated for imaging, it's going to be well collimated for visual.
I hadn't thought of that. So you take the diagonal off if you're going to do it visually.
Yep. For the most part, I will collimate with the camera because that's my primary use case. I did find with my 8-inch telescope, it was actually easier to collimate by eye because it's a short enough tube where I can have my eye in there and I can kind of tweak it I have Bob's knobs on my secondary mirror, so it's easier for me just to kind of feel out where the screw is and just kind of turn it. I tried the Bob's knobs on the 11-inch, but for some reason they were too stiff. I couldn't easily turn them with the amount of finesse that I needed to get good collimation. So the telescope came with Phillips head collimation screws. I swapped them out for Allen head screws. So I can get, I throw an Allen wrench in there and I can get really, really fine positioning on them. So the 11-inch I've only collimated via camera. The problem is the camera doesn't have as good of a dynamic range as your eye does. So things that are really bright versus really dim don't show up very well in the same frame in the camera, whereas your eye can see that bullseye and you can see all those diffraction rings all the way out. So in that sense, I've kind of learned that by eye can be superior because you're not dealing with the frame rate or the sensitivity of the camera. Your eye can see that much better. But it's also a lot more difficult to be looking while you're adjusting, whereas with the camera, you can see it on your computer while you're adjusting it much more comfortably. So I've got to try doing the 16-inch again because I've figured out with the 11 that even if I can't see the airy disk, if I focus out enough, I can start to see, rather than just the donut that you would typically get when you defocus an SCT telescope, as you get closer and closer into focus, that donut kind of collapses into a brighter bullseye. It's not the full airy disk bullseye, but there are still, the diffraction rings are close enough together where they do appear as a larger bullseye. And that kind of gets you rough collimation. You won't get the fine collimation until you can see the airy disk. But if you can at least get it close with those other bullseyes, that's usually good enough.
A comment and then two questions, Mark. A comment, first of all. I'm sitting here thinking that you almost wrote this presentation for me because I'm about where you were 10 years ago. The frustration of going out there and trying to capture images and fiddling with exposures and FPS and all the rest of it again.
Yeah.
And getting those smudgy images of Saturn and Jupiter and so on.
Yep.
So yeah, honestly, that picture you had there of Jupiter 2013 was me 2023.
Yeah. And yeah, like I said, I've been there, and that's kind of where you feel like you're at your limit because you're like, what else can I do?
Yeah.
And then once I learned about the thermal thing was a big thing because I didn't realize that you could have a localized atmosphere within a telescope tube. So that by itself is huge because you can't even think about collimating until you know those thermal currents are not an issue. The trick to the thermal currents, though, is you can kind of tell if your distortion is specifically in one direction. So if you're looking at that airy disk, so looking at that video on the bottom, this is a thermally acclimated telescope. If it weren't thermally acclimated, depending on which way is up in the telescope tube and where your camera's oriented, you'll kind of see what looks like a flame pattern, kind of like drawing air upwards, and that's kind of how you can tell it's a thermal issue and not just seeing.
Anyway, my two specific questions. Do you attach your camera to the back of the scope or to a diagonal?
The back.
All right, because I've been using the diagonal.
The diagonal is going to do some interesting things for the focal length. Because with the diagonal, the light kind of focuses at the mirror and then bounces back off. Mm-hmm. Whereas placing the camera directly in, you're focusing directly onto the camera surface. So I only really use the diagonal for visual just because I don't like breaking my back when I look through a telescope. But
makes sense.
Yeah, definitely put the camera directly on.
And the second specific, I wasn't being rude and doing Facebook and stuff when you were talking there. With Reggie stats, I saw you went through the process of doing the layers and so on. And I saw the main sliders and the denoising. I didn't see you touch the sharpening parameter.
Yeah, because the sharpening parameter only really helps if you already are starting with a really good image. Because sometimes what will happen, like with those moon images that I had really good seeing conditions for, I could max out these sliders and there'd still be room for more. So all this is really doing is, so like if I bump the sharpen up, it's effectively extending how far or how powerful each of those layers end up going.
Changing the ratio for the slider?
Yeah. Yeah. So like with the moon, I was able to bump that up to like 1.3 or 1.4. But if your base images aren't good to start with, it's not going to do you any good.
Then you have it to flang the sliders across to the right, do the denoising, and then adjust the sliders top down?
Yeah. Yep. And again, that's all personal preference and trial and error just to kind of see how things go. That's just kind of where I settled as far as like some people start at the bottom and work their way up. Usually for lunar images, I'll start at the bottom and work my way up. But for planetary, usually when I move this first fader, that's how I can tell if I had a good night or not. If I move that and I just get more blur, then I know either seeing wasn't good, my focus wasn't good, or there was some other issue.
I was happy blundering with this.
Yep. But the mantra "garbage in, garbage out" is like 1,000% true when it comes to planetary imaging. Because if your source images aren't good, you're not going to be able to process them down to anything good.
Mark, you were mentioning about thermal tube currents. This scope is at ambient air temperature most of the time because it's not heated. That's still a problem?
Oh yeah, just a couple degrees can make all the difference. Because the dome is still providing some amount of shielding from the outside air. So like it's generally warmer in the warm room. This air is going to seep under there, and it's going to go through the wall, and it's going to end up under there. So there is still a difference.
Because I can see if you had a scope in the house and then take it out, but this is...
Yep. That's why, like in the summer especially, it's always warmer under the dome than it is outside, especially at night. Because the dome heats up, because it's aluminum, that heat radiates inwards. And then when the sun goes down, the outside temperature drops 10, 15 degrees sometimes relatively quickly. But the air inside stays trapped until you open that aperture, and all of a sudden the cool air comes in, the warm air goes up, and it's problematic. That's why we have that exhaust fan, to try to help push that along quicker. And I think Jeff Miskey even modified the telescope. He cut a hole and put a little fan. So there's a fan on the telescope to try to help cool it quicker. But that's a lot of glass, and it takes a long time for it to cool down.
That's interesting. Thank you.
I have a question.
Yeah.
Here, right here in Regispecs, the file that you put in it, that you feed to Regispecs, that's already a still picture at this point.
Yes. Yep. Yeah. AutoStacker takes the video and does all the processing. Registax is capable of doing that,
Right.
but for some reason it has issues with the types of files that my camera produces. I'd have to convert it to a different file type for some reason. Or if the file is too large in size, like multiple gigabytes, Registax will immediately crash if you try to open it. Because, again, the program was written 15 years ago.
It's older than that, actually. I used it about 20 years ago.
Yeah.
In the days of using a
webcam.
As the camera.
Yeah, and that's kind of what started this whole lucky imaging thing. You know, that's what.
I have some halfway decent pictures. I mean, nothing like this quality, but of the moon and Mars when it was really close.
Yeah.
And Saturn as well, but yeah, not to that level. And it's like 90% of the settings you dealt with, I have no clue.
What's this one?
I remember just feeding an AVI file to Regispecs.
Yep. And that's still basically how it works. And that's, a lot of the camera manufacturers have kind of picked up on that too. And that's where a lot of the specialty astronomy cameras came from. They're all based on that webcam concept, where, the webcam may have internal gain or other adjustments. They take the same kind of sensor and just give you access to all those internal parameters to adjust it.
Sorry, a supplementary. That video clip for Jupiter, how long was that?
The one that I just fed into here,
Yeah.
I want to say, well, I can tell you. I go here and I open up the camera settings. So this was captured at 640 by 480. The full resolution of the camera is something like 1200 by 900 or something, but you can bin it down to get faster frames per second. It's raw 8. The exposure was 6.8 milliseconds. Gain was 316. Duration was 120 seconds at about 145 frames per second.
It was a 2-minute video.
Yeah.
At 145.
Yep.
When you say you pin it down, you mean you reduce the area that it captures from?
Yeah, not binning in the sense of like doubling up pixels, but more cropping. It's more area of interest than
Region of interest.
region of interest, right?
Yeah, yeah.
Yep.
And how do you relate the exposure time to the FPS?
Um,
Is it a direct ratio or?
to an extent. So the frames per second is defined by two things. Mainly the data transfer to the computer, like how fast the camera can physically pass data at the raw format. But the exposure time does play into that, because if your exposure time exceeds the number of frames per second, it'll end up dropping the frames per second. So I usually try to find that sweet spot of I'll try to find the exposure I want and see how it's affecting my frames per second. If I drop my exposure all the way to the lowest possible setting the camera can do, obviously I'm not going to see anything, but I can see what the maximum frame rate is theoretically. So if I'm exposing at 1,000th of a second and my maximum frame rate is 215, right? That's the fastest it can possibly move data to the computer. I'll try to find an exposure time what's my maximum exposure time to get that frame rate. And then I can adjust the gain to get the brightness to where I want it to be.
So the defining parameters of frame rate, and you back from that to exposure time, back from that to the gain.
That's one method. I mean, again, there's no one right way of doing this. I mean, this is just how I've kind of stumbled upon things. If I find, like for Saturn, for instance, Saturn is significantly fainter than Jupiter. So I can't use the same capture settings. I usually have to use much longer exposure times, like 10 to 15 milliseconds sometimes. Jupiter, I can get away with 5 to 6. I can try to increase the gain more, but eventually it gets to the point where the graininess is overwhelming, and I would need a significant number more images to make up for the graininess. So there's certainly a balance between gain, exposure, and frames per second.
Did you say you were using for Saturn?
Saturn, I usually target 10 to 15 milliseconds.
Okay. I've been using
it could still work. Really, you're just trying to optimize for seeing conditions. If seeing conditions are good, you can get away with longer exposure time because those moments of clarity last longer. But generally, the shorter your exposure, the better chance you have of capturing something that's decent.
Could you go over again how you determine seeing conditions? What parameters you look at?
Yeah. So the biggest place I go is the National Weather Service. I go down to current conditions, upper air. And this gives you maps of different altitudes. I think the 250 millibar level is somewhere around 35 or 40,000 feet. And this is what it looks like. Like tonight would not be a good night at all.
So you're just basing it on the wind speed.
Yeah.
And also, I imagine difference of wind speed and direction at different layers. Like if one layer goes like this and the other one goes like that.
Yep, that could also not be good. Yeah. Yep.
So now is that chart that you showed and then you picked the millibar level, is that a prediction or is that from radio sound?
This is radiosondes. So this data is only collected every 12 hours.
That's right.
So
0 and 12.
Yep. Yep. So yeah, to Bruno's point, if you look through the different levels, you can kind of see the direction of the wind. Like here, it's kind of blowing, up towards Canada, and at the 250 level, it's pointing almost due west, right? So yeah, that could also be a factor.
So where right now in the United States would be a good place to image from, based upon that map?
Today, Pacific Northwest, like Montana, based on the 250 level. If you come down to 500, yep, Montana still looks pretty good. 925, Montana still looks pretty good. And on the surface, yeah. I mean, for the most part, I find the desert Southwest has the most consistently good conditions. There's always like a big old high pressure system just kind of chilling there. And
We've got mountains to put the telescopes on.
then you got mountains to put the telescopes on. So, like one of the things I picked up from Damian Peach is he makes a pilgrimage, usually yearly to the Caribbean. He'll go to like St. Lucia or he'll go to, one of the Caribbean islands and he'll bring his 14-inch telescope. And he ends up collecting enough data there to process over the next couple of months. So like occasionally he'll post, a phenomenal Jupiter image that was taken, 3 months ago from one of the islands. So usually near opposition is when he'll go down there. So I think he went down there for the opposition of Saturn a couple weeks ago, and I think I don't know if he's going back for Jupiter, but we'll see.
Now about the seeing conditions, can we correlate anything from just recurrent weather that we perceive? Obviously not what it's like today, but you have is it better, for example, in summer when it tends to be hot and muggy, or on a negative temperature night in winter?
So
or
opinions
just completely unrelated.
Differ about this greatly, and the old adage is wintertime is better because the air is cooler and more stable, but the corollary to that is cooler air is also more dense. So, the denser air means you're looking through more, but it might be more stable. Whereas summer, it's hotter, it's less dense, but it could be more turbulent.
Humidity plays a role, you mentioned.
Humidity can play a role. That's more of a transparency issue than a stability issue. Sometimes, actually, I have found the best nights of seeing are when it's overcast. If there's a nice uniform overcast, like no individual clouds, I have, even though the transparency may not be good, the stability is excellent. So, like personally, I've had the best nights in early to mid fall. That's when I've seen the best seeing conditions. But it's also when the targets for Planetary are out at this time. Like Jupiter and Saturn now are in prime position as we approach fall into winter. I mean, that's not always the case. In 10 years, it might be Jupiter and Saturn are good in the spring.
And generally, the winds are a lot stronger in winter. Summertime, they tend to die off.
The other place I look, because that's only current observations, or at least current within 12 hours. Under forecast, under the severe weather, Storm Prediction Center has their HREF prediction, where this will try to predict 500 millibar winds out to a day and a half or 2 days. So like today it's Saturday, and what is it, about midnight UTC? So that means we are at about here. So this is what the 500 millibar should look like right now. And then I can kind of progress that forward and kind of see where things go. And there's not always a correlation between the 500 millibar and like the 250 or higher, but this is the only measure that actually has a prediction out, at least for the next 36 hours. So this is where I'll check first to kind of see if tomorrow's looking good, or the next day is looking good. Because typically when I see like look over Arizona right now, there's nothing. Like right at the California, Arizona, Mexico border, there's a big old piece of high pressure sitting there. So that would typically correlate with good seeing conditions. Again, you'd want to check day of the upper air maps, but when you see a big ridge like that, it usually means good things.
500 millibars is right about 18,000 feet. It's about half of the atmosphere.
Yeah.
Standard at sea level is 1013.2.
So yeah, this is a pretty good yardstick. Like the night that I predicted the good seeing conditions, there was a big old circle right over Connecticut, and that extended, out as far as North Carolina. And when I checked the upper air maps that night, so they get published at about 9:00 p.m. The 00 Zulu maps come out at 9:00, and it showed nothing. There was no wind at all in the upper atmosphere. Really rare. Yeah. That's why I said that I can count on one hand the number of really good planetary nights I get. So like, a night like tonight where, we've got all this blue and green at the 500 millibar level, and the 250 looked absolutely trash. This would not be a good night for planetary at all. It may not even be a good night for deep sky. Because for deep sky, when I'm using my guide scope, if those stars are twinkling, that guide scope's going to follow that twinkle. So I'll end up seeing way more guiding corrections as that star dances around. So depending on what I'm going after, if I'm doing a 5-minute exposure, that's not ideal because it means the scope's going to bobble all over the place.
And then when you get good seeing and good transparency, the Canadians send their smoke.
Yep. Which, again, could be an indicator of good seeing conditions. The other place you can check is GOES satellite imagery. Like to that point about the smoke. If the smoke is coming over, if you see if the clouds are booking it, if they're moving really quickly, there's a good chance there's a fair amount of wind up there, which is not good. So like some of the nights of poor transparency with the wildfires, you'd see the smoke just kind of lazily moving, which means that it's pretty stable up there.
So even with that smoke, you can still image?
Mm-hmm. You end up having to compensate a little bit. Like I'd have to either use more gain or higher exposure time, because if you lose that transparency, it means light's getting lost by either the smoke or the haze or, water vapor or whatever's up there. So I might have to bump up from 5 to 6.5 or 7 milliseconds to compensate for it.
So you lose the light intensity, but you don't lose the detail.
Yes.
Does that apply to planetary and deep sky?
To an extent. I mean, deep sky, you're already dealing with faint enough objects where if something is already faint enough where it has a low signal to noise ratio, or it's already, just beyond what even light pollution can see, if it blends in with the background, the transparency is really going to affect that. So if what you're looking at is already faint enough where you need hours of exposure just to see it, you're not going to be able to see it with poor transparency. So transparency matters way more for deep sky than it does for planetary. I thought I had copied the full resolution of the lunar mosaic here. That's the small one. No, I guess not.
On your lunar mosaics, Mark,
Yep.
how do you minimize the number of the overlap of your fields of view?
I just wing it. So with lunar, because I can see, I can identify certain features. I can say, okay, this crater is now on the left of the image. When I slide over, I'm going to make sure I have that full crater on the right of the image. And if my telescope is well aligned, it shouldn't drift too much. I mean, it'll inevitably drift some. But I just try to make sure that there's some identifiable feature between each image set, so that as I'm tagging, going across, going down, that there's something that overlaps.
Then when you put it back together, you do it just visually.
Mhm.
Okay,
Yep.
that's it.
Photoshop does have an automatic mosaic feature, but I found it ends up distorting things more than helping, especially with the C8 telescope. The focus is never like the full field. It's always kind of skewed to one side or the other, because the image projection is larger than or smaller than the area the camera picks up. So with the C8, I'll usually overlap more, and then as I'm stitching it together manually, I'll look at which images have sharper edges or sharper corners, or which regions of the image are sharper, and then I'll erase the blurry image and let it blend in. Less of a problem with the C11, I'm finding, because the C11 is a huge image circle, so I get to take advantage of the full size of the camera.
Do you mosaic east to west and then north to south, or
Nope. However I feel like opening it.
Shortcap doesn't have any mosaic tools.
It might, but I haven't played with them, if it does.
I know Nina does for Deep Sky. I don't.
Deep Sky's a little easier, though, because it aligns based on stars. You
Right.
can do some astrometric figuring, but with lunar, it's all visual, and especially because when you're stacking the images, it's going to stack whichever twisted version of the moon ended up presenting itself more often during that particular capture. So sometimes you'll find that a crater might be this big in one image, but this big in the next, and when you overlap them, you kind of rectify which one you want to use. So I'll find an edge of smooth regolith with nothing on it, and that's where I'll make the erasure. So it ends up being seamless.
Very nice, Mark.
Yeah, that
Thank
was
you.
excellent, Mark. Thank you. Thank you.